and then after work and energy, we will get into impulse and momentum. So I think you kind of know. We started out with a particle, and then we get into rigid body. We are studying the same thing, your work, your force, your energy, your impulse, your momentum, um, your velocity, acceleration. Okay, and we're looking at different systems. Studying is to be able to recognize the patterns, right? What's going on. So the best students are those who can pick up that differences in between systems, and you should be able to do that as quick as you can. So practice your brain. Brain is a very powerful thing. You can practice it. Don't let it stall. The only way to practice your brain is to read, write, draw, and yes, do that. Of course you can't exhaust it, meaning like you can't overwork your brain. So give it kind of like an exercise, right? Don't over exercise yourself. Do that, okay? So don't be lazy to do that. Also, don't do too much. Don't overdo. All right, so we'll get into of course linear and angular, momentum. Of course, this is like writing, really good for you, but another thing is to spot it instead of reading everything. Oh, we're gonna do linear, yes, and angular momentum. Then we're gonna hit on the principles. So again, linear and angular impulse and momentum. Like that. Okay. Because this is just a format of how we are going to study. So first you read your book. When you read it, don't put yourself too much into it. Just scan it. And try to recognize. Oh, these are the symbols we're talking about. Linear momentum and angular momentum, and we're studying a rigid body system. If you get it, that's okay. And then come back here and try to attempt this. Of course, I will give it to you here. So just saying like, oh, if we want to get the angular, so you're dealing with something that's rotating, so momentum. So see it rotating, two-dimensional rigid body. I mean, everything that we study are in two-dimensional because that's what we do, X and Y most of the time. If we give you another X, that'll be the end of the world. So just we stick to two-dimensional rigid body for a while. And of course, everything that we study is a reference from the center and mass, right? Because it's easier that way. So you know that regular momentum is your mass and the velocity. So the same thing, angular momentum is also mass and the velocity. But when you deal with the rotating stuff, then the mass is not called the mass moment of inertia, which is this guy. Because like I said, everything that is staying want to stay. So even though in rotation, things that want to stay try to stay, even if we push it, to go in a rotation. So right before that, you have the mass that's called the mass moment of inertia. It's adjustments and times, of course, your angular velocity. So therefore, you can just quickly spawn it right here. These things are all wrong because you're seeing the regular velocity inserted in it. So that's how you get rid of it, eliminate as soon as you see it. So you're left with this, and that's just a regular mass. You cannot apply the regular mass when you're dealing with the rotating stuff, angular stuff. Because and because of that, so we'll have to use the mass moment of inertia, with X like a mass. But of course, we're considering that it is subjected to some form of inertia on that mass. So that's how you would solve the MCQ stuff. So the difference in different student, I think, groups. So some student groups, they like to read a lot and then just try to remember. There's no need to remember. Use your brain. Okay, use your intelligence and try to understand. Doesn't matter what is given here. As long as you know what they are. Oh, I have two situations going on. One is a regular stuff, the other one is a rotating stuff. Rotating stuff, they always use the angular, that word. And regular stuff, we just the regular. So you have to differentiate your understanding that way. Okay, so the more you practice, exercise your brain, it will quickly see, whatever you're looking at or reading. Okay. Then the next one is, a rigid body is rotating upon an axis passing through the center of mass. Yeah, so the body is linear. See, linear momentum. Now you're given a rotating stuff, and then we want to talk about the linear momentum. So when you think about the linear momentum in the rotating stuff, of course that momentum is zero. Yeah, why? The momentum is mass and the velocity. So since it is rotating, your angular velocity and your mass moment of inertia, they took over the regular stuff. So when that is happening, your linear momentum, linear I mean we call it regular momentum, is at zero. It isn't happening. Okay, so therefore it's B. The rest of them are just giving you the formula for the angular momentum and then the linear momentum at point G. So it just, you can get rid of this right away. So you're subjected to only A and B. Yeah. So it can be constant because the rotation, in rotation, the angular momentum is overriding your linear momentum, and we assume that it's completely zero, for the linear momentum part. So therefore, it can't be constant. Then, of course, we get into the real life application right there, and we have this in this picture. You have a bridge, a swing. Actually, this is a swing bridge, not a regular one. So it opens and closes, So by turning, so we're going to use a motor located at A, which is right here. So without the motor, it can't be mechanically moved. You won't get the energy to move, meaning like set this into motion. So therefore, you need a motor, and the motor is located A to make this swing bridge open and close, of course. So the center of the deck, applies a torque, which is M right here, I'm showing you right there, little one right there, to the bridge. Torque is just a force anyway. So if the bridge was supported by rotated about, that is A and B. It will be down, so rotated right here, so it will open and close. So you gotta think about with the same torque open the bridge in the same time, or would it open slower or faster? So these are the things that we want to learn in this chapter. So what are the benefits of making the bridge with a variable depth structure shown? So right now you're gonna start to think about, okay, what's going on in this motion? Open and close. In order for this to open, because you always have a little, right, a support right there. That's the support where the center is, in order for, because when you look at the geometry, the geometry is just circular anyway, so you do have some form of rotation right here to open the swing bridge. So these are the things you want to think about before we get into the chapter, so you can design a better swing bridge design. So let's take a look at another application. We have a pendulum, your choppy tester. It's just a test, right? For this load, of course, it's gonna swing, down like this, going like up and down. So you're dealing with the angular momentum and then the linear momentum, they increase. And I want to go back here. Don't confuse with this one again. This is a completely different situation. This one is, we're talking about a rigid body about a fixed axis passing through the center of mass, all right, which is totally different from this situation. Okay, I gotta answer that right away because I know that the student will ask me about that. Here is a different setup. So here you have a pendulum, so your rotation is going that way. Yes, even the rigid body, how are you rotating? Okay, you're rotating that this way, because this thing is not rotating, that thing is rotating, which is attached to this. Okay, so very, very different thing. Yes, I just want to advise you to take it per situation, okay, and don't try to memorize everything. It would be a mistake. Of course, in this situation, you can be able to calculate the momentum, right? In the vertical position, because swinging this way, yeah, your distance from the center is D right here. Your G, yeah, my center is right over here. And of course, you have your regular, yes, linear momentum, and then your uh, rotating, which is your angular momentum here. Yeah, it's going that way. So this is happening at the same time. Okay. It is difficult for you to see. I remember one of the students had an issue on seeing. So when we draw on the 2D, it's a little bit difficult. Understand that it has a body. Okay. Of course, in this type of setup, we can be able to get the momentum and then also impulse. Yeah. Because of the time that this motion, the time this motion happening. Yeah, is we calculate. We can be able to calculate the impulse with it. Then we think about, oh yeah, since the pendulum is rotating about this point O, can we be able to calculate the angular momentum about that point O? Then of course we will learn how to calculate the angular momentum, right? And what type of equation that we use. You have to understand that you have nothing but a mass. Okay, mass is your object, your body, right? A particle. So rigid body, there is a mass, and when that mass moves, things happen. And how it moves, how long it moves, how is it moving? Yes, is it rotating or just translating or just going straight? So the path that it takes for that movement, yeah, we can calculate all of these things, yeah, quantities. That's what we're doing right here, yeah. Okay, so it's just the way that we're writing with all kinds of terms just confusing you. All right, um, all right. This is your space shuttle. Yeah, you know, because of the space shuttle and regular plane is not the same shape. They're different. Okay, this is the old version of one, old version answer stuff. So, you have several engines, and it's gonna make thrust. Of course, you need force to move this thing. This firing is nothing but with just making energy, yeah, enough energy to work it. So it would take a distance, yeah. So force taking a distance, we call it work. And with that work, um, you are making the you're making the motion, okay. And we of course we study everything about it because it is an event, yeah. So every event happen between two reference point. We gotta use a reference because otherwise it's impossible for us to measure them, yeah, measure and calculate. Of course the pilot is doing nothing, but the job of your pilot is to keep that, all right, in the route that we want to go, we want it to go, so it won't just go off here and there everywhere. So it's kind of like steering, yeah. The energy has already been automated, equipped. When you start it, it's gotta go. And with that energy, you have to take this thing to where you want to go. Yeah. So that's the job of your pilot. So of course you have two different engines going on, and we want to use only one engine. So engine means like you are making the energy in order for us to get this thing go in motion. So these are just questions. Yeah. Trying to understand the situation here given to you. So you think with it. Oh, if I use only like the engine A, yeah, about what axis this shuttle is going to rotate, things like that. Because if you use only one engine, then of course it's going to unbalance this thing, right? Because it is designed to be using different engines, yeah, by firing different engines. So if you're using only one, a single engine, then it might rotate, yeah, it's going to go off of the path. So these are the things you think about. So anyway, so let's go into here. So the very first thing that we're going to study is your linear and angular momentum. This is just your rigid body. We have seen it several times, yeah. You have your point P, See that right here? And you have your x, y coordinates, axis. And of course, since we put the point P right here at the intersection of x and y or endpoints, we call that the origin. It is called origin because you're measuring from here, like that, vertically and horizontally. And we've got point G. You should know what the point G is by now, another reference point that we measure things. So that point G, since it is in this body, you have a particular distance, for y distance, and also you have x distance, okay? So when you look at it, it is rotating in a counter-clockwise direction because of this arrow. Clockwise is in the opposite direction, okay? So pay attention to these little things. Okay, so we now know everything is right in here, G. This is just for breaking it down, breaking the force down. So the first thing that you have to know is your angular momentum, nothing but it's just your regular velocity times your mass, all right? That's, we call it the before we get into angular, we go into linear, linear momentum, and that's your L, another symbol, don't get confused, that's just a linear momentum. Since it is a momentum, you are looking at a mass going with a regular velocity, okay? Momentum is a vector because velocity is a vector, so you have a particular direction that is going. Your angular momentum, we're going to use our angular velocity, which is little omega right there, and then your moment, mass moment of inertia. The same thing, see, mass moment of inertia, velocity, angular velocity, L for linear, and H for angular momentum, okay? You can also write whatever you want to write, as long as you put a legend with it. That's all right. Of course, the direction of your angular momentum is going to be perpendicular to the plane of that rotation. Okay, so here rotation is happening this way. The plane of the rotation is like that. You can see it. You have to draw it that way. Just a plane. Translation, rectilinear and curvilinear translation. And your angular momentum is 0, at that time. So when this is in translation motion, either rectilinear or curvilinear, your angular momentum, right? Translation is overriding the rotation, so your angular momentum is 0. So we go H is 0, and linear is M with a V going, for this body right here. When you do a rotation, about a fixed axis, you're gonna pass through this little O point right here. Your body has linear and also angular momentum. Of course, we use the same equation, easy version of it, of this course, so you don't get confused. Linear, angular, linear mass, angular mass, moment of inertia, velocity, angular velocity. Pretty easy. Sometimes, you'll have to use this equation, but that's just the same thing because we're using a different way of writing. So when you see this, we're talking about momentum. That's the momentum, and that's the momentum. That's why you can add together, It's just giving you, I want to get the momentum at point O. In order for us to get the momentum at point O, if you're given momentum at point G, you will have to combine that two things, So first, we get the momentum, right, at point G, which is this. Then we're going to account for the your regular, linear momentum part, which is mvg, and that is about r, distance away. So this 2 point O and G is r distance away from each other. See that? So you add them up, all that momentum together, so you will get the momentum up here. So if you want the momentum up here, You have to find the momentum here. The momentum here, two part going on. One is a regular, yeah, with velocity. The other one is an angular velocity at that point. Two momentum going on. Okay, so you're gonna add this, and this linear momentum is about this distance away, yeah, from the point G. So if you want to get the point O, we get that. If I move the point O to here, the only difference is your distance is different, so that is going to be different. Okay, that's about it. See, yeah. If you know how to read the equations, everything comes like so easy to you. All right, we do the same thing, general planar. So we're gonna think about both, right? You have linear and angular because translation or rotations are happening at the same time for general plane of motion. Okay, so we put them again the same thing. Now angular momentum here about your G, yeah, point, and then another, right? Linear momentum is there. The distance, yeah, is about D. So one of the students having issue with the point A is this point A can be anywhere, yeah. And we usually get the distance. I think at that time, like he couldn't be able to see. It's always okay, perpendicular to each other. Okay, we're gonna try to get this one. Yeah. So the distance you will measure from here to here. Yeah? Of course, you can use your Pythagoras theorem. You can also use a regular measurement. Yeah. So it depends on the condition given to you. What's most important here is for you to be able to see momentum can be, you can calculate the momentum at any point A, yeah, by measuring from the point G. All you have to do is just add all momentum. Rotation, yes, momentum due to rotation. And the other one is momentum due to translation. Momentum due to translation use a regular velocity, yeah. And of course, that point at this point is always a distance away from each other. Try to get that. Don't worry about any of the Pythagoras condition, things like that, okay? I will give you this distance. So it's easier for you to calculate. All right. This is just listen because there's a calculus part in it. We won't go into minute changes like this. This is just showing you the time change is very small, yeah? Of course, when you look at it, you have to understand that motions are happening, yeah, at different motions at different times. Therefore, you can say like one particular motion is going with the same velocity. They don't, yeah. So it depends on the time and how the way the body is moving, what kind of stuff in the environment is affecting on that body's motion. Everything is instantaneous and happening, again, to reference point, yeah. So here we're just giving time as a reference point here, reference point 1 or 2. This event is going on, and it didn't happen only between that, yeah, interval. When you go beyond that, it didn't happen. Okay, so I mean this condition didn't happen before T1 and after T2. Something else, yeah, a different motion will happen. That's all I want you to be able to understand it. Yeah, if you get it, it's pretty good because a lot of the people can't be able to see it. Yeah. So here we're thinking about a particle motion and your impulse and also momentum. They happen as soon as your body is in motion, yeah, regardless of that body is a rigid body or a particle. So we're gonna have to combine, yes, the equation of the motion, and we call it the kinematics. Kinematics mean, hey, we're dealing with everything that is moving, things that you need to add them up in order for us to get the total result in, yeah. So that's about it. And we do it all the time when we have to deal with the force of a mass, velocity, and of course we're studying between two reference points, and we call that time, yeah, time. It's just a measurement. Time is a measurement. It's not an existence, a measurement, okay? Now we're looking at the activity happening between that two reference points. don't try to memorize this. I'm not going to ask you. Yeah, if you could get the concept, that's all right. Of course, we usually use a diagram because for us to be able to understand, so our brain tends to forget what we read. So it's better like we draw it out, in our diagram, so that way we don't forget what we're given. So anyway, if you can see that, oh, this is an impulse diagram, we are adding. You can't add the things that are not the same. So when you see the equation and adding, subtracting, you know that they are the same, quantity, even if we write it in a different way. So we have an initial momentum, then we have an impulse diagram, and this too is going to give you the final, momentum. See, the same thing going on. Initial, something happened, and you got final. Initial, something happened, you got final. Whether that's a velocity, acceleration, or momentum and impulse. Okay, impulses we're looking at, very time, very small time changes. Okay, so if the motion is happening and we're dealing only with the x-y coordinates anyway, they come with the plane. It's the same thing. So when you apply that to the xy direction, your angular momentum, okay, angular momentum, angular impulse, it's just impulse and momentum we're studying at the same time. So that can happen along your z-axis, okay, passing through. And when we talk about z-axis, meaning that we're just taking a point, usually our reference point, your mass center, which is your g, okay. Why g is easier to calculate that way, because all the points have a different velocity and stuff. So we just take the center, it's kind of, we feel like it's a very balanced point, even though it isn't, depends on the shape of your body, And here, when we do the impulse and momentum together, usually we use the diagram. Something, you have initial thing, another thing happened, we're gonna add them all together to get the final, So try to get that big picture. And of course, you are dealing with a value, so it's always a scalar, even if they do have direction, because your momentum is based on your velocity. Velocity has a direction, All right, procedure for analysis, we'll just read through this, okay? So here is a procedure for analysis, and we usually study with the XYZ axis, and we draw the diagram. For momentum and impulse, you always have to deal with the mass, because without the mass, there's no body. If the mass is rotating, we call that the mass moment of inertia, because as soon as the body rotates, that mass is different. Like I said, nothing in the world is connected permanently. They're all like aggregations, okay, in a system. So therefore, when the body as a whole moves, everything inside of us moves. Okay, that's what's going on when we take a point like that. To simplify, we usually take the center point G. So all our measurement goes from it. Even if you pick a point somewhere else, we always measure from it. Okay, so if you want to get the momentum somewhere else, you still need to account for what's going on at that center. Why? Because our calculation based on that reference point. Okay, so when you try to calculate something, they situate in different location. Of course, there's a distance, between them, and we will also account for that. So at least you have to get all of that, items in a big picture. And we use, of course, kinematics equation, dealing with the mass center, dealing with the angular velocity, and also dealing with the linear, velocity in it. Okay, the very first example, we have a wheel. Everybody has a mass, so 300 kilogram. Since this is a wheel, you have a radius. Since we're dealing with the point O, it's the radius of gyration. Since it is a radius of gyration, we use K as a symbol, 0.4 meter. Don't confuse this with the elastic constant, the spring constant. So the wheel is subjected to a couple moment, okay, 300 Newton meter. So this is your moment that's been given to you. So we have to find the angular velocity of that mass, right? And the time references, we're going to deal with the 6 seconds apart, yeah? Starting from the rest and go 6 seconds. When you think about the frictions, external forces, no slipping, meaning like the body is in balance to do that motion, yeah? All right, time as a parameter, mean time as a measurement, yeah? And we are going to think about how to get the impulse momentum, and then from there we're going to bridge it to the angular velocity. So first we draw our diagram. We're going to add this and this to get the final initial, and something happened, and then the final. So what's going on? Definitely, rotation, translation, because here regular, and then that's the angular, and then you have distances, because you have a r, radius, because we have a central point, your point G, in there, and right now we're calling that center point, okay, as O here, so don't forget your O and G. G is the automatic mass center, O is a point that we choose. Sometimes they can overlap, sometimes they're far away from each other, and now we start going on with our first, bridge between the irregular and then the angular, because we know R, yes. We have to find the angular because it's, when you look at it, look here, we're given the moment right here, Newton meter. In order for us to go to the angular velocity, we need this, okay? That's what we want to know. So first, we have to find angular velocity, yes? So anyway, so we won't get into this, okay? If you know like how we're calculating, you should be able to know that. So the angular velocity is equal to this, and then we're going to put into each one of them, the very first one is your momentum, and then this is a change, to that momentum. So see, very, very carefully, you can be able to see the regular, momentum, and the angular momentum, yes, is equal to your, mt. This is just a change in the impulse and momentum, showing that. So you will get the final of that, and then plug it in everything that we know into it, and you're going to get your angular velocity, okay? Since we're not given the velocity, yes, directly in your question, your regular velocity is not given, we'll have to get it from what we are given, which is your k, which is this, radius of gyration. So that's what we're trying to do. Since we don't know the g, we have to use something else, which is this one, see that, putting right over here, yes. And then of course we know the I, that's the mass moment of inertia, yes, from your k, because it's given the here radius for you, not the regular radius, the radius of gyration right here, and then your another angular velocity, and then the rest of them are just mathematics, okay? Okay, the next one is just a little multiple choice. So you have a slab, and that slab is rotating. Again, every time we rotate about the center of mass, which is the mass center, G, or point G, and angular momentum about any point. A point can be anywhere, and you got to compare, that to either that's a larger or less or the same, The two is angular momentum computed about here. So you have your 2 points, angular momentum right here, angular momentum right there. You compare it, okay? So every time you compare it, G and P, and it's talking about the angular momentum, of point G. And you have also the angular momentum of that, yes? Since we're not given any other information, it's the same, So if you have like a particular V or something subjected to it, then it will be different, So like I said, it depends on the situation. You can take it like right away, So the angular momentum about here is the same as the angular momentum of the point P. linear momentum. Then we go into regular linear momentum. Yes. So you gotta look into the first problem. It doesn't say anything about translation or general plane motion at all. It's only that it is rotating. So therefore, it's overriding the linear movement. That's why you don't have a VG. Yes, to to disturb this same angular momentum. Both of the points are going together because it is in totally in rotation motion. So therefore at that time your linear momentum in this situation is zero. Okay. So how do you know whether you gotta have a V or not? It depends on your diagram. The diagram didn't say anything about V, so therefore it's zero. All right. um, Then we'll get into two little gears right there and attached to each other, so therefore the energy is transferable. That's, you gotta get it right away. And then of course, you have your weight is given here. Your K is given there for you. Radius of gyrations, and then of course your M, which is your impulse. Is feet-pound is given to you as well, and we'll have to get your angular velocity for the gear A. Okay. Of course, here we're dealing with some time when the two gears rotate, together. So let's take a look at how we're gonna find the angular velocity at A. So we have an impulse momentum diagram. We draw it. We're given the weight. Okay, this is just showing you there's a force, and the time, so you can be able to get other quantities at the axis and then break that force, into two different coordinates. Don't worry about it. Won't be asking you this. Just listen, and you're dealing with the rotation. Gear B, weight is different. A and B right there. See the differences? That's just showing you the change happened in a very small time. And we have of course the force, and we break the force down, and you have your rotation, which is your angular rotation. And we need to find this gear A angular velocity, this one. They are again in balance is because they're connected to each other. So therefore energy can be transferred. So we go into angular impulse and momentum relation, which is this. You start with the A here. We put in everything that we understand or given here, which is your moment mass. This is your momentum for angular momentum, with your angular velocity here divided by some distance away from that force, making the gear rotating. For gear B, of course, it's in contact with that, and we have the same thing. Okay, that's just a change in that time 1 to 2. Okay, that's just a reference point from this second to that second. Of course, we do our math. Again, this is just for you to understand. Okay, when we do the reducer problem, we usually use this equation, because the angular velocity at A, this distance away from the center, is conserved. The angular velocity at B, distance away from that B center, they're the same. And that's why they can work together. When one gear is rolling, the other gear rolling with the same energy. So that's what's talking about. This is the most important thing for you. The rest of them we just put in, plug it in, the information we need. Don't worry about the calculus part. All you need to know is we're trying to get the angular A, angular velocity at A. I sometimes say like angular A, okay? And of course we move everything around and plug it in and calculate, and you will be getting that. Okay, so what is most important thing for you to know is this. Okay, is conserved. All right, then we'll get into a little quiz right here. So you have a slender bar rotates about an A, angular momentum with respect to A since we're dealing with the angular momentum, yeah, you're gonna take a look at it. Yes, angular momentum is always right. You have your angular velocity, so they all have it, and you have a moment mass of inertia. Okay, so when you take a look at it, the only moment mass, right, that you can deal with is actually you have all of it. Okay, so ml2. Don't worry about it. I won't be asking you that. But in this case, okay, so when you look at it, you are dealing with the fraction here. Yeah. So since you have to understand that the point is right here, yeah, or right there, okay? So that's about half, yeah? And you are not given half here, yeah? That's one, that 1/6, 1/12 is too small, right? So if you move that, it's going to be like a different, yes, place that can go. Mass doesn't change, yeah? So that got to go proportionally to this length right here, yeah? So therefore we chose the closest one, which is 1/3, yeah? Not accurate, but that's kind of like your SAT question, yes? So these little things, yeah, that you can find the exact answer sometimes in some of the questions, but don't freak out about it. Get the closest one. So questions like that try to ask the student if you truly understand everything in the world that we have studied so far, are dealing with whether you are close, yeah, to the truth or not. So just playing with the accuracy stuff, yeah. And there's no such thing as an exact accurate thing. Only the truth is happening around something. Yeah. So yeah, we don't have a 1/2. So the closest one is 1/3. Okay. Is that the exact thing for that situation? No, but it's good enough. Yeah, because I have bad stuff here, which is if this can't happen, that's kind of a little bit, yeah. And this is the worst, right? Of course. Anyway, so then let's go into 2A. Principle of work and energy. You work, you have energy. Then you can do the work. With the work, we can go motion. Yeah, we can move our stuff, ourselves, or something else. So if a force does no work, yeah, meaning like the force is not strong enough to move something into motion, so it does not need to be shown on the impulse and momentum diagram. That's not true. Yeah, you can still draw the diagram regardless if the force doesn't work or not. We can still put it, yeah, in the diagram. So that's force, of course. And then we go into the next section. It's reading, yeah. So you get another one right here. If there are no external impulses acting on a body, what is it going to be? Are we dealing only with the linear momentum conserved or angular momentum conserved? Yeah, impulses is just a change in that motion in a particular time, very very small time. Yeah, the same thing. So your so we cannot just, yeah, this two will go out right away because it said only linear, only angular. It's not true because we're dealing with a body. If that's a body, the body can be subject to linear and angular, yeah. So therefore when no external impulses happen, of course it's C, yeah. Even if you don't even remember the momentum or anything, but you gotta understand the body going either linear or rotation, okay. Motion can happen at the same time. So you can get rid of A, B, and D like straight. So the only thing that left is C. D is wrong because it said neither. Yeah, no, that's wrong. You have, yes. And these two conditions only when you identify the situation of that body, how the motion is going, yeah, in the problem. Otherwise, we can't assume, because you can't assume that the angular is zero or linear momentum is zero at all when you're not given any kind of information. See, like these little things. So science is very important because we take it as it is. We don't like fabricate or add or bias. Yeah, you have to take it as it is and train yourself if you want to keep yourself, science, engineering, technology, and mathematics. Yeah, why? Because we have to take things as they are without changing it. so we can understand what's going on, yeah, as true as possible to that situation. Okay, so if a rigid body is going to rotate, every time you rotate, there is an axis passing through the center of mass, of course, yeah. Your G is always there. The body's linear momentum, yeah, is going to be zero. Why? Because it is in rotation only, yeah. All right. This is just application linking to the real world situation. Your skater, spend a lot of time spinning on the ice, practicing, so you won't, she won't go off balance. Rotating through the air, you spin fast for a long time. The skater, that motion, she's get enough angular momentum. Yeah, with that, she doesn't even need to exert more energy. Just keep going. Yeah, automatically. Yeah, it's you feel good. Yeah, in the motion if you try. So if the skater angular momentum is constant, can the skater vary her rotational speed? Okay, so if you want to keep that angular momentum constant, and can you vary the rotational speed, and how do you do that? So the skater spin faster, the arms like drawn, go up, right? Drawn in, and slower when the arms are extended. Okay, that's because the body mass, if you keep them all together, is faster. So if you change the shape of the body, extend it outside like a disc, then it gets slower. Yeah, so spear is always faster than the disc. Application, another one over here, we have a conservation of angular momentum allows cast to land on this feet, and divers to flip. Yeah, so he is rolling like that, rotating like this, twist the spiral and then turn. Of course, it's gonna help, right? This person make that spin. This is in a lecture hall, and that's the instructor is showing you the rotation like that. Do fun things like that. So the conservation of angular momentum is going to make the water, suckle the drain faster, and it gets closer to the drain. There's some form of water right in there that he is rotating. Okay. So, anyways, right here you understand that when you have a rotation going on, you're dealing with angular momentum, and your conservation of angular momentum, can happen. Of course, if you have like the two systems going on in touch, So right now, this rotation, and there is a water, cycle drain is right down there. Okay, you can see it. Not a very good picture. This is another problem that you're not responsible for getting into it. Here we're using the conservation of linear momentum, and when you look at it, don't feel bad about looking at it. It's just a symbol. It's just showing you can get the final, this is a linear impulse momentum relationship. Yes, so you can get the final, right, momentum from the initial momentum if you have some changes, some form of impulse changes right in there. Or you have to just add it up. That's all you see. Of course, you can write the linear momentum in this way with a regular velocity right there. Your initial, so we put it 1, final, so we put it 2 right here. And this can be 0 in some situation, like this. So if the sum of all the linear impulses acting on the rigid body is 0, the impulse terms are also 0. So the linear momentum for that rigid body, initial and of course the final, they are conserved. Okay, meaning like if we don't take about the what's going to change the momentum to get a final, this change part, no change has happened at that time, you're conserved. So that's what is the linear momentum conservation is about. So conservation of your angular momentum, the same thing. See, the symbol is different. Initial and the final, we put it into, instead of h, we write it in real, mass, momentum, inertia, and angular velocity. Of course, we write it that way. And then when this impulse part is 0, no impulse, of course, so we can get they're the same, 0, this is 0, also this and this the same. The initial and the final, angular momentum are the same. when we think about the momentum, we're thinking about the mass moving with a velocity. Okay, mass moving with a velocity at the same time. All right, procedure for analysis, you don't need it. We usually break it down to x, y, z. Yeah, then we think about our linear momentum conservation equation. Yeah, then we'll get into dealing with your center G. Yeah, and from that you can be able to get wherever you want to calculate either velocity. Yeah, from velocity, if you want to branch it to acceleration, you can do that too. Yeah. All right, the 10 kilogram, your wheel again. Yeah, and here your mass is given to you in the form of mass, moment, mass of inertia. And then of course this is rolling, no slipping, so in balance and taking the motion in that way. Yeah, it won't rebound, meaning like bump and then come back on. So, and we need to find the velocity again, minimum velocity that your wheel, okay, needed to roll over. And there's a little obstruction right here because the surface changes. See the bump, a little bump A here, and that happened about 0.03 meter. Okay, all right. So how are we gonna get it? We start with the diagram. We're gonna put in all of our impulse momentum diagram, your momentum, your impulse, and then your final momentum. And then we're gonna plug in everything that we're given. Yes. And then from there we will calculate. Yes. We're gonna calculate because the question asks you the regular velocity. Okay. So in order for you to get the regular velocity, you have to write the regular velocity. Yeah. And put in everything we're given. Yes. Of course, you don't know what the angular velocity is. It said there's no slip, so angular velocity is equal to our famous equation. Yes, your r omega is equal to v. Yes, and we're gonna put that into there all together. Yeah, because we know the r right here given to you there, 0.2. Yeah. So 1 divided by 0.2 is going to give you this. And then put that back in here to this equation, W, omega, and you will get this. So anyway, I won't ask you this complicated one. We'll just do the easy one for you. And of course, we do the conservation of energy since you're dealing with the motion. Yeah. So our kinetic energy, yeah, and your potential energy, we put them all together in. So we put our work energy here, work energy conservation right there. You'll put our kinetic energy and the work, all together in there. Since you have a disturbance right here, your velocity for the second condition is going to be 0. Yeah, that's where you can see. And plug everything back in here, and you will get that. In position 3 and 2 is just showing you the in a very small time this V is going to go over that disturbance. Yeah, so position 1 going up, position 3. Okay, so the V is going to go to position 3 from 2, and when that happened, even if you have a disturbance, it doesn't change, meaning like you use the same energy, to go from this point to that point. So therefore, we can use this energy conservation equation to be able to get that regular velocity out of it. Okay. Again, I won't be asking you this, but if you have an interest, you can look over it. But I do want you to understand that there is a conservation of energy every time we deal with emotion. Yeah. And of course, we go into here. We look at this concept, because again, you have a slender round, so mass, it is at rest, and then you have a bullet, and that's fire with a velocity coming in, angular momentum of that bullet about a, okay, just before the impact. So impact means it's hitting, in a small amount of time, disturbing that balance. So the distance away from this motion to our reference point A is 0.5. So you have a mass, so there is this, okay? You can't choose this because the mass is just without any kind of distance. We do have a reference. The reference is from A. So therefore, B and D just go, straight out. So when you look at it here, we're dealing with the angular momentum, when you take a look at it here, see, mass is the same, 0.5 is the same. The only thing that is different is the velocity. This one is square and that one isn't, So therefore it is A, because mv is your momentum. We're dealing with the momentum linear, So therefore it's got to be just v, not v squared. See, how easy to choose it. So for the rod in the question 1, the angular momentum about, again, A is your reference point of the rod, the bullet just after the impact. So right after the impact, what's going to happen? Of course, you're going to conserve, everything that happens. So we're dealing with the final stuff. So when you take a look at the final stuff, D is out right away. It can't be 0. You still have the motion. So you do have a momentum, So this one is out too, because the momentum is 0.5 distance away. So we have B and C right here, right there. So now I have a 3 condition happening. This one is only 2 conditions happening right here. And we're dealing with angular, so they're all angular, They're all angular right there. But when you pay attention to that, this thing is just out of sort, right? Because we don't have that kind of term. When you think about the impact, so that's usually mass and your angular velocity, with some distance. Usually we square it, okay? So right now you don't know about this. I won't ask you that one. So that's where B and C difference. I would just get rid of C because there's no square on it, so it can't be true, That's got to be only this two. That's just a formula checking for you. All right, go back to the next one. You have a mass under G. 3 pound, it's your, ball right here, and the velocity is given to you, regular one, 6 feet. We're in British system. Some people call it English, and that's fine too. So when I strike, at the end of the smooth, 5 pound, slender bar right here, which is initially at rest. And we want to try to find this angular velocity of the bar, not the ball, but the bar, about the z-axis, okay? Just after the impact of E is going to be 0.8. We did learn how to do this on these on E in last week equation. It's just a conservation momentum, by the way. I will be asking you again. It's just like I want you to take a look at how we calculate, kinematics. We use the same equation here, which is your V equal to R times your angular velocity. It's just a different way of writing it. We start with the bar, try to get, British, unit. The first thing you try to get is, the z-axis, and you need your mass, moment of inertia, which is your mass, by the way. You need it. Without that, we can be able to calculate, the momentum of it. So that's why we first calculate that. Then we're going to use a conservation of angular momentum equation, and we're going to put our angular momentum in terms of the regular velocity, because they're asking you the regular velocity. So this is the connection between the angular and the regular velocity. And then since you're dealing with the angular, we're going to write in terms of the regular velocity. And from there, we get this equation. And from here, we calculate, your VG, which is the ball and the bar. From there, we're going to put that back into our angular and linear velocity relationship equation, which is this one. Back into it, and you will end up getting your angular velocity. Okay. Again, I won't be asking you that. If you know how it flows, it should be okay. All right. Now we're gonna end with this quiz. We're gonna use a conservation of linear and angular momentum. So if we want to use it, what do we need to do? So if we're dealing with the linear and angular, of course, you have to have a linear and angular impulses, got to sum to 0. Otherwise, you can't get rid of that part of the impulse which is usually added to the initial momentum, yeah, situation to get final situation. As long as you have impulse, you can have the conservation of your initial equal to your final, yeah, angular momentum or linear momentum together. So therefore, the answer is C right here. Both linear and angular impulses got to be summed up to 0, yeah, for the conservation of the initial and final situation to happen for both linear and angular momentum. And the next one is the angular momentum of a body about a point A going around in a fixed axis of rotation, yeah, but not the mass center G, yeah. So when you look at it again, dealing with the angular momentum, so therefore there's a two, yeah, different place right there here. So we can say like both A and C, yeah, we can do that because that just this is just a one, yeah, point. There is another G point, but your question is saying it's happening two axes, fixed axis, and then the mass center, yeah, point A and G, yeah, see. So therefore just A is wrong, just G is wrong, and this said both A and C. A is wrong, so how can it be A and C is right? So this is bang 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 gone. Yeah, so therefore even if you don't know the formula, C is correct. Yeah. So when you look at it, of course, that's a regular part and that's your angular part happening, yeah, in a 2 point. And we're just writing it in terms of this regular point is representing the point A, but we're writing the point A angular, yeah, the velocity in the form of regular velocity, that distance away from that G, okay? You always have a distance away from each other every time you have a point, which is not the G point, yes, because you're measuring that point is this amount, yeah, radius far away from that G, and there is a angular momentum, and then of course a rotation happening at that point. So therefore you also have the regular momentum and the angular momentum, since you can't add two different things together, so you have to change that, yeah, into angular. Because when you look at it, this is angular because we're putting this in terms, yeah, of that. We have seen this again and again for this meaning, like, yeah, there's a distance between point A and G, yeah. So you can solve it with the elimination, yeah, process of elimination, or you can choose it by actually knowing it. Alright, that's it for this chapter.